Every star you have ever seen in the night sky is temporary. The sun will burn for another 5 billion years, then collapse. The stars beyond it will follow, one by one, across timescales so vast that the entire history of human civilization would not register as a single heartbeat against them. Eventually, after hundreds of trillions of years, the last star will exhaust its fuel and go dark, and then the waiting begins. Because dead stars do not simply vanish, they leave behind remnants, dense, cooling objects that go on existing long after their light is gone, drifting through an increasingly empty universe, cooling slowly for trillions upon trillions of years. Given enough time, those remnants cool completely. They stop emitting heat. They stop emitting light. They become something that has never existed anywhere in this universe. Not once, not yet. Something so cold and so dark that no instrument we have could detect it. A black dwarf. The universe is 13.8 billion years old. That sounds ancient. By the timescales required for a black dwarf to form, it is barely a beginning. The first one will not appear for approximately 1 trillion years. Every star burning anywhere in the observable universe tonight will have to live out its entire life, and its remnant will have to cool for an almost incomprehensible span of time before a single one exists. But here is what makes this more than a story about darkness and cold. According to current physics, the very last black dwarfs, the ones that survive longest into the dying universe, may not simply fade away. In a cosmos where almost nothing remains, where galaxies have long since dispersed, and the night sky has been dark for longer than stars existed, something may still happen to them. One final event in a universe with almost nothing left to witness it. Physics allows us to follow this story an almost unimaginable distance into the dark, and what it finds at the end is stranger than the darkness itself. Quick favor before we continue. If you find yourself coming back to videos like these, hit subscribe so you don't miss the next one. It makes a bigger difference than you might think. Let's talk about what we actually know. Everything in this story begins with an ordinary point of light. Look up on any clear night, and every star you see appears steady, distant, and unchanging. Yet each one is locked in an immense struggle that determines how long it will exist and what it will eventually leave behind. To understand the last dead star in the universe, we first need to understand what a star truly is. Despite the familiar glow, a star is not burning like wood in a fire or wax in a candle. Deep inside its core, gravity squeezes hydrogen atoms together with such overwhelming pressure that they merge into helium. This process is called nuclear fusion, meaning lighter atomic nuclei combine into heavier ones. During each fusion reaction, a tiny fraction of mass disappears, transformed directly into energy. That energy pushes outward as light, heat, and radiation, beginning a journey that may take thousands of years to escape the star before racing across space. Our own sun performs this astonishing feat every second. It converts about 4,600,000 tons of its own mass into energy during each passing moment. Even at that extraordinary rate, the sun contains enough fuel to continue shining for billions of years because its total mass is so enormous. A star survives through balance. Gravity constantly pulls every layer inward, attempting to compress the entire object into something smaller. Fusion pushes outward with equal determination. As long as these opposing influences remain evenly matched, the star holds its shape and continues producing light. If either side ultimately gains the advantage, the star changes forever. Long before that balance exists, the story begins inside a nebula. a vast cloud made mostly of hydrogen drifting between the stars. Over immense stretches of time, gravity gathers portions of that cloud into denser clumps. Material continues falling inward until the growing center reaches roughly 49 million degrees Fahrenheit. At that temperature, hydrogen nuclei begin fusing, and a newborn star finally ignites. From that moment onward, one characteristic governs almost everything. Mass decides how hot the star becomes, how brightly it shines, how rapidly it consumes its fuel, and how its life concludes. The largest stars live brilliant but comparatively brief lives. Smaller stars burn with remarkable patience, stretching their existence across trillions of years. When fusion finally ends, every star follows one of only a few possible paths. Some collapse into neutron stars. The most massive become black holes. Stars with masses similar to our Sun leave behind white dwarfs, dense stellar remnants that no longer create new energy through fusion. Every black dwarf described in this journey begins as one of those white dwarfs. Our Sun belongs to a class known as a G type main sequence star. At roughly 4,600,000,000 years old, it stands near the midpoint of its life. Its future will shape everything that follows, because by tracing the fate of this familiar star, we also trace the path toward the final stellar remnant the universe will ever know. There will come a day when the sun rises for the last time over Earth, although by then there will be no oceans left to reflect it, and no living landscape beneath its light. Its end is already written into the physics of its core. Roughly 5 billion years from now, the hydrogen fuel that has sustained our star for billions of years will finally be exhausted, and the stable balance that has defined its life will begin to unravel. Without fresh hydrogen fusion in the core, the outward pressure weakens. Gravity immediately gains the advantage, drawing the central regions inward. As the core contracts, it grows dramatically hotter until temperatures climb to nearly 180 million degrees Fahrenheit. Under those crushing conditions, helium nuclei finally begin fusing into heavier elements through an event astronomers call the helium flash, an explosive ignition buried far beneath the sun's outer layers. The scale of that release is astonishing. During only a few minutes, the helium flash produces as much energy as the sun currently radiates across roughly 100 million years. Yet if you could somehow observe the sun from a safe distance, you would notice almost nothing at first. More than 430,000 miles of dense stellar material blankets the eruption, absorbing the violence before it can reach the surface. Deep within, everything is changed. The renewed fusion alters the star's internal structure, allowing the outer layers to swell outward. Over time, the sun expands until its diameter reaches between 100 and 200 times its present size. It has entered the red giant stage, becoming vastly larger than the familiar star we know today. The inner solar system pays the price. Mercury disappears first, consumed within the swollen atmosphere of the expanding giant. Venus follows. Earth faces an equally unforgiving future. Surface temperatures climb beyond 4,800 degrees Fahrenheit. Oceans vanish into space. The atmosphere escapes. Even solid rock softens and begins to flow under relentless heat, erasing every mountain, continent, and trace of the world that once supported life. Curiously, the visible surface of the enlarged sun becomes cooler during this transformation. Its temperature falls from roughly 10,000 degrees Fahrenheit today to about 5,800 degrees Fahrenheit. Even so, its immense size gives it a far greater total brightness, allowing it to pour vastly more energy into the surrounding solar system than before. Expansion also weakens the sun's hold on its own outer atmosphere. Those distant layers drift farther from the core, where gravity grips them less securely. Streams of gas begin escaping into surrounding space, carrying away material that had remained bound to the star since its birth. The sun is gradually shedding part of itself, changing from a stable furnace into an object preparing for its next state. Compared with the immense timescales we have already explored, this entire chapter passes remarkably quickly. Only a few 100 million years separate the beginning of the red giant phase from the moment the sun starts giving its remaining matter back to the galaxy that formed it. Eventually, the swollen sun can no longer hold itself together. Helium in the core becomes increasingly scarce, and the star enters a period of repeated instability. Instead of remaining a single, coherent sphere, its outer atmosphere begins lifting away in broad, expanding shells. One wave follows another, each carrying enormous quantities of gas farther into surrounding space until the star is gradually stripped of nearly everything beyond its core. Astronomers call the resulting structure a planetary nebula, although the name tells a misleading story. In the year 1785, the astronomer William Herschel noticed that several of these glowing objects resembled the pale disks of distant planets when viewed through early telescopes. The resemblance ended there. They have no connection to planets at all. They are the illuminated remains of dying stars, suspended across interstellar space like enormous expanding clouds. During this transformation, the sun will release roughly 40 to 50% of its original mass. That material spreads outward across several light years, carrying hydrogen, helium, carbon, oxygen, and countless other atoms forged or preserved during the star's lifetime. For a comparatively brief span of about 10,000 years, the escaping gas shines vividly as intense ultraviolet radiation from the newly exposed core energizes every drifting shell. Gradually, the expanding cloud grows thinner. The radiation weakens, and the glowing veil fades into the surrounding darkness. You can already see this process unfolding elsewhere in our galaxy. The Ring Nebula, located about 2,283 light-years from Earth, displays the delicate circular structure left behind by a sun-like star nearing the end of its evolution. The Helix Nebula, about 650 light-years away, reveals another example, with intricate filaments tracing the motion of gas released long ago. These are not distant curiosities. They are windows into the future of our own solar system. Nothing expelled during this stage is wasted. The drifting material mixes with the galaxy's vast reservoirs of interstellar gas, enriching future stellar nurseries with heavier elements unavailable during the earliest chapters of cosmic history. Every carbon atom that helps build living cells, every oxygen atom carried in water, every calcium atom locked within bone has passed through one or more ancient stars before reaching its present home. Stellar endings become the raw ingredients for future beginnings. As the final layers drift away, only the exposed center remains. Almost the entire atmosphere has vanished. Fusion has ceased. The object left behind measures only about the size of Earth, yet it contains more than half the sun's remaining mass packed into that remarkably compact volume. Its surface blazes at extraordinary temperatures, while its interior has become one of the densest forms of ordinary matter the universe allows. This remnant is called a white dwarf. From this point onward, the story is no longer about a living star, but about the enduring fate of its stellar core. What remains after the sun has surrendered its outer layers hardly resembles the star that once anchored the solar system. The brilliant furnace is gone. Fusion has ended forever. In its place sits a compact stellar remnant called a white dwarf, the exposed carbon and oxygen core of a former star, carrying the memory of billions of years of nuclear fusion without producing any new energy of its own. Although the Sun will lose much of its mass during its final stages, the surviving core will still contain about 54% of the Sun's present mass. All of that matter will be compressed into a sphere only about 7,900 miles across, giving it a diameter remarkably similar to Earth's. Imagine placing more than half the mass of the Sun inside a world no larger than our own planet. The resulting density stretches ordinary experience beyond recognition. Even the smallest sample becomes astonishing. A single teaspoon of white dwarf material would weigh roughly 15 tons if it could somehow be brought to Earth intact. That is comparable to the weight of a fully loaded pickup truck compressed into the volume of a sugar cube. Matter itself has been packed to an extraordinary limit, leaving almost no empty space between its particles. You might expect such an object to collapse even further under its own immense gravity. Surprisingly, it does not. The support holding a white dwarf together comes from something called electron degeneracy pressure. In simple terms, this is a consequence of quantum mechanics, the branch of physics governing the smallest particles in nature. According to a principle discovered by the physicist Wolfgang Pauli, no two electrons can occupy exactly the same quantum state at the same time. Inside a white dwarf, electrons are squeezed so closely together that this fundamental rule resists any additional compression. This resistance is unlike the pressure produced by hot gas or expanding radiation inside an ordinary star. It arises from the underlying architecture of the universe itself. The white dwarf survives because matter has reached a point where quantum mechanics refuses to let gravity push any farther. At the moment of its birth, the surface of the Sun's white dwarf will still blaze at roughly 180,000 degrees Fahrenheit. Its brightness comes entirely from heat left over from its previous life. No fresh energy is being created. The remnant simply radiates away the thermal reserve accumulated during billions of years of stellar activity, gradually becoming dimmer across immense spans of time. Our galaxy already contains approximately 10 billion white dwarfs. Every one represents the final chapter of a once ordinary star. They differ in age, temperature, and composition, yet they all share the same destiny. Each is slowly releasing the last traces of stored warmth, following a path so gradual that none has yet reached its ultimate state, even after the entire history of the universe so far. If you could somehow watch a white dwarf across billions of years, you would notice something deeply unexpected. It does not simply cool from blazing heat toward darkness. Hidden beneath its bright surface, the interior gradually changes state. The star's remnant begins to crystallize, transforming from an ultra-dense fluid into an immense, solid structure unlike anything found naturally in today's solar system. The pressures inside a white dwarf are almost beyond imagination. Near the center, they rise to roughly 10 million times greater than the pressure at Earth's core. Under those extraordinary conditions, carbon and oxygen atoms can no longer drift freely as they once did. As temperatures continue falling, the atoms settle into an orderly crystalline lattice, a repeating arrangement extending through the stellar interior with remarkable precision. Chemically, that crystal is the same form of carbon that we recognize as diamond. The difference lies in scale. The Sun's future white dwarf will eventually contain a crystallized core roughly the size of Earth, making it the largest diamond-like object our solar system will ever produce. Although its interior also contains oxygen woven through the lattice, the underlying structure follows the same physical principles that create gemstones beneath Earth's surface. This description is far more than an appealing comparison. Evidence arrived through observations made by the European Space Agency's Gaia Space Telescope. During the year 2019, astronomers studying Gaia's measurements noticed an unusual concentration of white dwarfs occupying a specific region of the Hertzsprung and Russell diagram, a chart that compares stellar brightness with temperature. The only explanation matching the observations was crystallization occurring inside these ancient remnants. As the crystal forms, it releases latent heat, meaning energy liberated during a change of state rather than from nuclear fusion. That additional warmth slows the overall cooling process. Instead of fading at a steady pace, the white dwarf lingers for roughly 2 billion extra years while its interior continues solidifying. Even in death, the remnant briefly resists its own gradual decline. The transformation begins at the center, where pressure is greatest. Over immense spans of time, the solid region expands outward layer by layer. Billions of years pass before the process reaches the outer portions of the star. Nothing happens rapidly. Every new shell joins the growing crystal through an almost imperceptible progression governed entirely by physics. More massive white dwarfs crystallize sooner than lighter ones because their stronger gravity produces even higher internal pressures. Their dense interiors encourage atoms to lock into place earlier, allowing the crystal to spread more efficiently throughout the remnant. Less massive white dwarfs follow the same path, although their transformation unfolds more gradually. The next time you see a diamond catching the light, consider what gives it that remarkable structure. It is simply carbon arranged by immense pressure into perfect order. One day, our sun will leave behind that same fundamental architecture, expanded beyond planetary scale, preserving the final record of a star that once filled the solar system with warmth. Most white dwarfs spend their remaining existence slowly releasing stored heat. Yet, that future is not guaranteed. A single number determines whether one of these stellar remnants endures for unimaginable ages or vanishes in an explosion of extraordinary power. That number is 1.4, a value that transformed our understanding of how stars live and die. The story behind it began during the year 1930. A 19-year-old physicist named Subramanian Chandrasekhar was traveling by ship from India to England. During the voyage, he filled notebooks with calculations exploring what would happen if a white dwarf continued gaining mass. Working inside his cabin, he reached a conclusion that many established astronomers initially rejected because it challenged accepted ideas about the limits of matter itself. Chandrasekhar discovered that electron degeneracy pressure cannot support an unlimited amount of weight. Quantum mechanics provides remarkable resistance against gravity, yet even that resistance has a boundary. Once a white dwarf reaches approximately 1.4 times the mass of the Sun, the supporting effect fails. Astronomers now call this threshold the Chandrasekhar limit in recognition of the scientist who first calculated it. Beyond that limit, gravity overwhelms the remnant with astonishing speed. The star collapses inward so rapidly that temperatures and pressures rise catastrophically. Carbon fusion ignites throughout the interior almost simultaneously, producing an uncontrolled thermonuclear explosion. Unlike an ordinary star, which can survive ongoing fusion for billions of years, the white dwarf is completely destroyed within moments. Nothing resembling the original object remains. Astronomers classify this event as a Type 1, a supernova. For a brief period, the explosion can shine more brightly than an entire galaxy containing hundreds of billions of stars. Elements forged during the blast are hurled across interstellar space, enriching future generations of stars and planets with heavier matter created during the final seconds of the white dwarf's existence. These explosions became valuable for another remarkable reason. Because type 1 supernovas reach nearly the same peak brightness every time, astronomers use them as standard candles, objects with known luminosity that allow reliable measurements across enormous cosmic distances. During the year 1998, careful observations of these explosions revealed that the expansion of the universe is accelerating rather than slowing. That unexpected discovery pointed toward the existence of dark energy and ultimately led to the Nobel Prize in Physics awarded during the year 2011. A white dwarf does not usually cross the Chandrasekhar limit alone. Most often, it belongs to a binary star system where two stars orbit one another. Over millions of years, the white dwarf gradually steals gas from its companion. Each new layer adds mass until the critical threshold is crossed, ending the long accumulation in complete destruction. Those that remain isolated avoid this fate entirely. Without a nearby companion feeding additional matter onto their surfaces, they never approach the Chandrasekhar limit. Their slow cooling continues uninterrupted across spans of time that exceed the present age of the universe many times over, preserving the only path that ultimately leads toward a black dwarf. There is a remarkable detail hidden beneath everything we have explored so far. The object at the center of this story has never actually existed, not once. Across the observable universe, despite its countless galaxies and staggering population of stars, no black dwarf has yet had enough time to form. We are following a destination that physics predicts with remarkable confidence, even though nature has not reached it. The reason is surprisingly simple. White dwarfs cool at an extraordinarily slow pace. Once fusion has ended, they possess no new source of energy, yet the immense reservoir of heat trapped inside them leaks away with astonishing patience. Current theoretical models estimate that a white dwarf requires somewhere between 1 quadrillion and 100 quadrillion years before it cools enough to become a true black dwarf, an object that has radiated away essentially all detectable thermal energy. Now compare those spans with the age of the universe itself. Modern observations indicate that the cosmos is approximately 13 billion to 800 million years old. Even the shortest estimated journey toward a black dwarf lasts roughly 72,000 times longer than everything that has happened since the Big Bang. The universe, vast as it already seems, is still remarkably young compared with the lifetime of these stellar remnants. The oldest white dwarfs we can observe today formed when some of the earliest generations of stars reached the ends of their lives roughly 10 to 12 billion years ago. After all that time, they remain surprisingly warm. Their surfaces still measure around 3,600 degrees Fahrenheit, hotter than the surfaces of many living red dwarf stars that continue producing energy through nuclear fusion. They have cooled considerably, yet they remain far from complete darkness. Imagine compressing the entire cooling process into a single calendar year. Within that scale, everything since the beginning of the universe would occupy only about the first 7 minutes after midnight on the first day of January. Almost the entire year would still lie ahead. That comparison captures just how little of the journey any existing white dwarf has completed. Because of this immense disparity in time, every white dwarf in the observable universe remains in the earliest stages of its long decline. Each one continues releasing stored warmth into space. None has crossed the final threshold. None has yet become the cold, stellar remnant described by theory. Even so, the process is already underway. In the Milky Way alone, roughly 10 billion white dwarfs are gradually following the same path, each governed by identical physical laws. Their cooling cannot be hurried or interrupted by ordinary means. It simply unfolds across intervals so immense that human intuition struggles to accommodate them. Perhaps that is one of theoretical astrophysics' greatest achievements. By applying the known laws of gravity, quantum mechanics, and thermodynamics, astronomers can describe an object that has never been observed, estimate its properties, predict its evolution, and understand its place in cosmic history long before the universe itself has grown old enough to create the first example. Step back from any single white dwarf, and an even larger transformation comes into view. While countless stellar remnants are slowly releasing their stored warmth, the galaxy surrounding them is changing as well. The Milky Way is not a permanent engine of creation. It is steadily consuming the very material required to produce new generations of stars. Today, our galaxy forms only about 1 to 3 new stars each year. That may sound substantial, yet it represents a long decline that has continued for billions of years. Every newborn star begins inside a cold molecular cloud, a dense region where hydrogen gas gathers under gravity. Those clouds are a limited resource. Each new star locks away part of that supply, leaving less raw material available for the future. Although dying stars return some matter to space, much of it never returns to the cold, dense conditions needed to begin the process again. Long before the galaxy reaches that distant future, our own world will face a far earlier change. As the sun gradually grows brighter during the next 1 to 2 billion years, Earth will drift beyond the habitable zone, the region around a star where liquid water can remain stable on a planet's surface. Oceans will disappear, and the familiar conditions that once supported life here will come to an end while the Milky Way continues its much longer evolution. Meanwhile, another galaxy has been approaching all along. The Andromeda Galaxy now lies about 2,537,000 light-years away, moving toward us at roughly 70 miles per second. Around 4,500,000,000 years from now, the two great spiral galaxies will begin merging into one immense system. Despite the dramatic scale of that encounter, direct collisions between stars are extraordinarily unlikely. The distances separating individual stars are so vast that most simply pass one another. Computer simulations suggest the Sun has roughly a 50% chance of being scattered into a completely different region of the newly combined galaxy, carrying any surviving remnant of the solar system into unfamiliar surroundings. Over the following billion years, the merger settles into a large elliptical galaxy, sometimes called Milkomeda. By then, much of the available star-forming gas has already been exhausted. New stellar births become increasingly uncommon, while white dwarfs, neutron stars, and black holes steadily accumulate. As trillions of years pass, the brightest stars disappear first because they consume their fuel most rapidly. Small red dwarfs inherit the galaxy. The least massive among them burn so efficiently that some continue shining for nearly 10 trillion years, providing the dominant source of starlight long after stars like the Sun have vanished. Even that era eventually ends. Astronomers estimate that the final new star within the Milky Way's region will ignite roughly 100 trillion years from now. After that moment, no fresh stellar fires will ever begin there again. The galaxy will continue to exist, yet it will do so with an ever-growing population of ancient remnants and an ever-shrinking supply of living stars. By the time stars like the Sun have all completed their lives, the universe has not reached an ending. Instead, it enters its longest chapter, The brilliant blue giants have long vanished. Yellow stars have faded into compact remnants. Across the galaxies that remain, another population quietly assumes the role of carrying almost all surviving starlight. These are the red dwarfs, the smallest and most enduring true stars ever formed. A red dwarf contains less than half the mass of the Sun. That modest size changes everything about its existence. Lower gravity creates lower temperatures in the core, allowing nuclear fusion to proceed at an extraordinarily measured pace. Rather than consuming fuel rapidly, these stars stretch their hydrogen reserves across spans of time that dwarf every earlier era of cosmic history. Within the Milky Way, red dwarfs already make up roughly 70 to 75% of all stars. They are the galaxy's most common residents, although many remain too faint to see without powerful telescopes. The smallest among them are expected to survive for about 10 trillion years, nearly 1,000 times longer than the universe has existed so far. Perhaps the most remarkable fact is that none has ever reached the natural end of its life. Every red dwarf that has formed since the earliest ages of the cosmos continues shining today. The universe itself is simply too young for even the oldest examples to have exhausted their fuel. Astronomers understand how their stories will end through well-established physics, yet no observer has ever witnessed one die of old age. Their extraordinary longevity comes from an unusual internal structure. Unlike the Sun, which fuses hydrogen mainly within its central core, while much of its outer material remains untouched, a red dwarf is fully convective. That term means hot material rises while cooler material sinks throughout the entire star, continually circulating fresh hydrogen into the fusion region. Almost the entire supply of fuel eventually participates in generating energy, making these stars astonishingly efficient. Imagine looking upward, roughly 5 trillion years from now. The familiar mixture of brilliant white, yellow, and blue stars has disappeared. Nearly every point of light belongs to a red dwarf, each glowing with a deeper color and a gentler brightness than the stars surrounding Earth today. Any civilization still present would inherit a sky that appeared noticeably dimmer, with only these enduring crimson suns scattered across the darkness. Eventually, even their patience reaches its limit. After approximately 10 trillion years, the smallest red dwarfs finally consume the last usable hydrogen within their interiors. Without fusion to sustain them, they contract and settle into white dwarfs, joining the countless stellar remnants already waiting across the cosmos. With that transition, the familiar age of living stars comes to its natural conclusion. No new stars remain to ignite because the raw material needed to create them has long been exhausted. None continue burning through nuclear fusion. From that point onward, the universe is illuminated only by the lingering warmth of ancient remnants, each slowly yielding the final traces of energy inherited from a far more luminous past. Imagine arriving after every ordinary star has completed its life. The familiar pattern of stellar birth and stellar death has ended, yet the universe remains populated by countless surviving objects. Cosmologists call this immense span the degenerate era, a period extending from roughly 10 trillion years until about 100 quintillion years into the future. It is defined by what remains after fusion has almost entirely disappeared from cosmic history. Across space, white dwarfs continue their gradual cooling. Neutron stars endure with astonishing density. Brown dwarfs persist as failed stars that never became massive enough to ignite sustained hydrogen fusion. Rogue planets wander between galaxies after gravitational encounters expelled them from their original systems. Black holes anchor the deepest gravitational wells. The universe is far from empty. It is crowded with remnants carrying the accumulated history of earlier ages. What has changed is the source of light. None of these objects create fresh energy through ordinary stellar fusion. The great furnaces that once transformed hydrogen into heavier elements have all gone out. Every remaining glow comes from stored heat, gravitational effects, or occasional collisions rather than ongoing stellar life. The cosmic energy budget steadily declines as each remnant releases the last traces inherited from a much brighter universe. Even the ancient afterglow of the Big Bang continues fading. Known as the cosmic microwave background, this faint radiation presently measures about negative 454.76 degrees Fahrenheit. As space expands, its wavelength stretches ever farther, carrying its temperature downward across unimaginable stretches of time. It never disappears entirely, yet it becomes increasingly difficult to distinguish from the surrounding cold. Motion, however, never completely stops. Binary white dwarfs continue orbiting one another while emitting gravitational waves, ripples in spacetime, predicted by Albert Einstein, and later directly detected by observatories on Earth. Those waves slowly rob the system of orbital energy. After enough time, the two remnants spiral together and collide, briefly producing a thermonuclear explosion that interrupts the long fading of the surrounding cosmos. Brown dwarfs follow a different path. Because they never achieved sustained hydrogen fusion, they spend their existence radiating the warmth produced during their original gravitational contraction. Over trillions of years, that reserve gradually diminishes until they become increasingly difficult to detect. Nearby, rogue planets continue crossing interstellar and eventually intergalactic distances, no longer belonging to any solar system or circling any star. The galaxies themselves also begin losing their identity. Repeated gravitational encounters between stellar remnants slowly scatter members into intergalactic space through a process called gravitational evaporation. During roughly 10 quintillion years, most of the former inhabitants of a galaxy are eventually flung away, leaving behind an ever thinner collection of objects. Structures like the Milky Way gradually dissolve until little remains except the immense supermassive black hole that once occupied the galactic center, lingering within an expanding universe that grows steadily more diffuse with every passing age. As the ages continue unfolding, the balance of the universe shifts once again. Galaxies lose their structure, stars disappear, and familiar landmarks fade from existence. Among all the surviving objects, black holes gradually become the dominant presence, not through constant activity, but through extraordinary endurance. They remain after almost everything else has surrendered to time. The smallest stellar black holes, formed from the collapse of massive stars, typically contain between 5 and 20 times the mass of the Sun. Despite their violent origins, they spend nearly all of their existence changing very little. Current calculations indicate that a typical stellar black hole can persist for roughly 10 to the 67th years before finally disappearing. That span exceeds every earlier chapter of cosmic history by an almost unimaginable margin. Even more enduring are the supermassive black holes that occupy the centers of galaxies. At the heart of the Milky Way resides Sagittarius A star, containing approximately 4 million times the Sun's mass. According to present theoretical models, an object of that size may survive for somewhere between 10 to the 83rd and 10 to the 87th years. During nearly all of that immense interval, it remains one of the largest organized structures left in the universe. Yet black holes are not truly eternal. During the year 1974, The physicist Stephen Hawking proposed a remarkable prediction that united gravity with quantum mechanics. According to this idea, empty space near the event horizon, the boundary beyond which nothing can return, constantly produces pairs of particles that briefly appear before disappearing again. Occasionally, one particle falls into the black hole while its partner escapes into space. The escaping particle carries away a minute amount of energy, causing the black hole to lose an equally minute amount of mass. This process is known as Hawking radiation. Today, that effect is almost impossible to notice. The Hawking temperature of Sagittarius A star is approximately 0.00000000000015 Kelvin, vastly colder than the surrounding cosmic microwave background. Because the universe itself remains warmer than the black hole, it absorbs more radiation than it emits. Only after the cosmos cools, much further does evaporation begin to dominate. Once that long transition finally unfolds, the black hole shrinks with increasing speed. The final stage arrives surprisingly quickly compared with the ages preceding it. After enduring for perhaps 10 to the 83rd years, the remaining mass converts into a brief release of high-energy radiation and particles, including gamma rays. The universe witnesses one final burst before another ancient structure disappears forever. With the evaporation of the last supermassive black hole, concentrated objects have almost entirely vanished. Cosmologists describe what follows as the photon era, a future filled primarily with diffuse radiation and elementary particles spread across an ever-expanding cosmos. Amid that immense simplicity, the oldest white dwarfs are finally completing the cooling process that began unimaginably long before, becoming the first true black dwarfs in a universe where almost every other source of structure has already passed away. Now that we have crossed the immense stretches of time leading here, the object itself can finally be described in full. A black dwarf is the ultimate destination of a sun-like star, the final state reached after a white dwarf has released essentially all of its stored thermal energy. It is not a different kind of stellar remnant. It is the same remnant, carried to the furthest possible endpoint by time alone. Its physical properties remain almost entirely unchanged. The mass stays the same. Its diameter remains comparable to Earth's. The extraordinary density established during the white dwarf stage also survives intact. Electron degeneracy pressure, the quantum mechanical effect that prevents further collapse, continues supporting the object exactly as it did before. Only one property steadily changes across those unimaginable ages. Temperature continues falling until it becomes almost indistinguishable from the surrounding universe. Near that endpoint, the surface approaches absolute zero, approximately negative 459.67 degrees Fahrenheit. According to the known laws of thermodynamics, absolute zero itself cannot be completely reached, yet the remaining warmth becomes so small that it no longer produces detectable thermal radiation. The black dwarf has surrendered virtually every trace of heat inherited from the ancient star that created it. Its interior has also completed a transformation that began billions upon billions of years earlier. The crystallization spreading outward from the center has finally reached every remaining layer. The entire object becomes a solid crystalline mixture of carbon and oxygen, preserving the immense diamond-like lattice formed under extraordinary pressure. What was once a blazing star now exists as a fully solid, planetary-sized crystal suspended within the expanding universe. By this stage, ordinary observation becomes almost impossible. The object generates no visible light. It emits no meaningful infrared radiation. In an era where nearly every luminous source has already disappeared, there is effectively nothing nearby to illuminate its surface. Without incoming light to scatter, it reflects nothing toward a distant observer. Against the background of an aged universe, the black dwarf becomes essentially invisible. Yet, despite that apparent emptiness, its internal structure remains astonishingly intact. It is the densest form of ordinary matter that can exist without collapsing into something even more extreme. No planet, moon, or conventional solid object approaches its density. At the same time, it has not become a neutron star or a black hole because electron degeneracy pressure still balances gravity with unwavering stability. If you could somehow drift beside one, there would be almost nothing to witness. No changing weather, no glowing surface, no continuing chemical activity. The black dwarf has reached a state of remarkable stillness while remaining a genuine physical object. Even then, the story is not completely finished. The forces capable of altering a black dwarf no longer come from stellar evolution or gravity. They arise from processes buried deep within atomic nuclei themselves, operating according to quantum physics across intervals of time so immense that the black dwarf will have endured for incomprehensible ages before the first signs of change can finally emerge. If time alone determined the fate of a white dwarf, its journey toward becoming a black dwarf would seem straightforward. Heat would simply flow outward until none remained. Nature, however, proves far more intricate. Several independent physical processes interrupt that gradual decline, each delaying the loss of energy by millions, billions, or even trillions of years. Together, they stretch stellar cooling into the longest transformation known in ordinary stellar evolution. The earliest stage unfolds, while the white dwarf still possesses a surface temperature above roughly 18,000 degrees Fahrenheit. At those tremendous temperatures, much of the escaping energy leaves through neutrinos, nearly massless particles that interact so weakly with matter they can pass through an entire star with only the slightest chance of being stopped. Because they escape so efficiently, this opening phase represents the fastest period of cooling. As the remnant grows cooler, another process gradually takes over. Once the surface falls below approximately 18,000 degrees Fahrenheit, photons become the primary carriers of energy. A photon is a particle of light, and unlike neutrinos, photons repeatedly interact with the dense stellar material before finally escaping into space. Every interaction slows the outward flow of energy, reducing the overall cooling rate and extending the lifetime of the white dwarf. The pace changes again when crystallization begins deep inside the core. As the carbon and oxygen interior transforms into an ordered crystal, the change of state releases latent heat, energy produced during the transition from one physical form to another. That additional warmth temporarily offsets part of the continuing energy loss. Instead of cooling smoothly, the white dwarf lingers in this stage for roughly 2 billion extra years while the crystal steadily expands. Gravity also contributes in an unexpected way. During crystallization, heavier oxygen atoms gradually settle toward the center, while lighter carbon atoms migrate outward. This rearrangement, called chemical differentiation, releases gravitational potential energy. In plain terms, matter moving into a more stable arrangement converts a small amount of gravitational energy into heat, providing another subtle source of warmth that delays the overall decline. Even trace ingredients continue participating. Tiny amounts of heavier elements, such as neon and sodium, remain from the original star that existed long before the white dwarf formed. Across immense intervals, those atoms slowly sink through the dense interior. This process, known as sedimentation, also transforms gravitational energy into heat, adding another small contribution to the remarkably prolonged cooling history. The final mechanism belongs to an even stranger realm of physics. At extraordinary density and extremely low temperature, quantum tunneling allows certain atomic nuclei to overcome barriers that ordinary thermal energy can no longer cross. These rare events, called pycnonuclear reactions, produce only the faintest trickle of heat, yet they persist in conditions where conventional fusion has long since become impossible. Viewed together, these processes reveal a remarkable pattern. Quantum mechanics, gravity, chemistry, and the behavior of matter under immense pressure all work against the steady loss of heat. Rather than allowing the remnant to cool uninterrupted, each mechanism delays the inevitable, combining to create a journey toward the black dwarf stage that lasts longer than any other known chapter in the life of an ordinary star. Long before the final black dwarfs appear, their future has already been shaped by gravity. The decisive events do not happen during the last stages of cooling. They occur while the remaining stellar remnants are still passing through the final echoes of galactic evolution, gradually separating until companionship itself becomes exceedingly rare across the expanding universe. Over roughly 10 quintillion to 100 quintillion years, gravitational evaporation steadily dismantles what were once recognizable galaxies. Each close encounter between stellar remnants transfers tiny amounts of orbital energy. Given enough time, those countless interactions gradually accelerate individual objects beyond the weakened gravitational grip of their home systems. One by one, white dwarfs, neutron stars, brown dwarfs, and black holes depart, following independent paths into intergalactic space. Among those travelers, the white dwarfs most likely to complete the journey toward becoming black dwarfs share an important characteristic. They are alone. A nearby companion could transfer matter onto the white dwarf, potentially triggering renewed activity or even a catastrophic explosion. Repeated gravitational encounters could alter its orbit or send it toward another remnant. Complete isolation removes those possibilities, allowing the cooling process to continue without interruption for incomprehensible spans of time. Picture one of these stellar remnants after its long departure. There is no surrounding spiral galaxy. No glowing star clusters remain nearby. The familiar architecture of cosmic neighborhoods has dissolved into distances almost beyond description. The white dwarf continues forward through intergalactic space along a path determined billions upon billions of years earlier, encountering essentially nothing capable of changing its course. As expansion continues, the separation between these isolated remnants grows ever greater. Eventually, the nearest neighboring objects may lie billions of light years away, farther apart than entire galaxies are from one another today. At those scales, the concept of a local environment begins losing its ordinary meaning. Each remnant follows its own history, governed almost entirely by the physics contained within itself. The object destined to become the very last black dwarf has already begun its story, although it bears little resemblance to its distant future. At this moment, it has almost certainly not even entered the white dwarf stage. It is still a small red dwarf, steadily converting hydrogen into helium with extraordinary patience. Before cooling can even begin, it must first complete the longest stellar lifetime known, then spend additional ages releasing its remaining heat. When that distant remnant finally reaches the black dwarf state, everything that surrounded its birth will already have vanished. Its original galaxy will have dispersed. The galactic cluster that once held neighboring galaxies together will no longer exist as a recognizable structure. Even the immense black holes that occupied ancient galactic centers will have completed their own astonishingly long evolution. By then, isolation is no longer an event unfolding around the remnant. It has become the defining condition of its existence. The idea of a neighboring star, a nearby galaxy, or even a familiar cosmic landmark has faded beyond relevance, leaving the last black dwarf to complete its extraordinary transformation within a universe where distance has become the only enduring landscape. There is one final possibility that does not arrive from outside the black dwarf. No passing star disturbs it. No collision interrupts its course. Instead, the next challenge may already exist within every atom making up its extraordinary crystal interior. After surviving the deaths of stars, galaxies, and even black holes, the remnant may ultimately depend upon the stability of the proton itself. A proton is one of the fundamental particles found inside the nucleus of every ordinary atom. Together with neutrons, it forms the dense central core around which electrons exist. Everything from planets and mountains to your own body depends upon protons remaining intact, yet modern physics has never proven that a proton must exist forever. Since the year 1996, the Super Kamiokande Observatory in Japan has searched for evidence that protons eventually break apart. This enormous underground detector monitors an immense volume of ultra-pure water for the characteristic flashes expected from such events. After decades of observations, no confirmed proton decay has been detected. That absence is itself an important scientific result. If protons do decay, present observations indicate they survive for at least 10 to the 34th years. Even so, many theoretical extensions of the standard model of particle physics suggest a different future. Among the most influential are grand unified theories, mathematical frameworks that attempt to unite several fundamental forces under a single description. Many versions predict that protons eventually decay across timescales, ranging from about 10 to the 31st through 10 to the 36th years, although no experiment has yet confirmed those predictions. Should proton decay prove real, every ordinary atom ultimately comes apart. The proton transforms into lighter particles, including positrons and pions. Those products rapidly decay further or annihilate with surrounding particles, releasing energy during the process. Matter does not vanish instantly. Instead, it gradually unravels through an almost unimaginably slow sequence of microscopic events. Within a black dwarf, that process creates an unexpected source of warmth. The remnant no longer depends upon fusion or stored thermal energy. Instead, the gradual destruction of its own atomic structure provides a faint internal furnace. If you could somehow observe such an object across these impossible ages, it would produce an exceedingly dim glow generated by quantum processes unfolding deep inside its crystalline interior. Calculations suggest that a black dwarf affected by proton decay would eventually lose all of its ordinary matter after roughly 10 to the 37th years. By then, nothing recognizable from the original white dwarf would remain. Every atom composing that ancient stellar remnant would have been transformed into lighter particles and radiation. An intriguing possibility also remains. If the shorter predicted proton lifetimes are correct, decay begins influencing some stellar remnants before cooling has completely finished. The object would already be dissolving while still approaching the black dwarf state. If, however, protons are perfectly stable, then the black dwarf survives this entire chapter unchanged, carrying its pristine crystal structure into an even more remote future governed by stranger laws than particle decay alone. Among all the endings we have explored, one possibility stands apart through its astonishing timing. It does not happen while stars still shine or while black holes still dominate the cosmos. Instead, it belongs to an age so remote that almost every familiar structure has already disappeared. Yet some of the most massive black dwarfs may still possess enough hidden potential to produce the last supernovae the universe will ever experience. This remarkable prediction was developed by physicist Matt Kaplan of Illinois State University and published during the year 2020 in the journal Monthly Notices of the Royal Astronomical Society. His calculations describe a sequence unlike any supernova observed today, arising inside objects that have remained cold for spans of time beyond ordinary imagination. The driving mechanism is called a pycnonuclear reaction. Earlier, we encountered the name without exploring its full consequences. In plain language, the extraordinary density inside a black dwarf allows atomic nuclei to fuse through quantum tunneling rather than intense heat. Quantum tunneling is the ability of particles to cross barriers that classical physics would forbid. Even at temperatures approaching absolute zero, two nuclei occasionally merge because the strange rules of quantum mechanics permit an exceedingly rare pathway unavailable under everyday conditions. Those individual reactions occur at an almost immeasurably slow pace. Across immense intervals, however, they gradually reshape the interior. Carbon and oxygen fuse into heavier elements. Neon follows. Magnesium appears after that. Silicon eventually forms as the process continues through countless generations of rare nuclear events. Every step unfolds within the compressed crystalline core, while the black dwarf outwardly appears unchanged. The sequence eventually reaches iron. That moment changes everything. Iron occupies a unique place in stellar physics because fusing iron requires more energy than it releases. Once iron begins accumulating, nuclear reactions can no longer provide support through additional energy production. The growing iron core steadily approaches a critical threshold deep inside the ancient remnant. Eventually, electron degeneracy pressure can no longer sustain the increasing weight concentrated at the center. The same quantum mechanical force that preserved the white dwarf and later the black dwarf finally yields. Collapse begins, followed almost immediately by a thermonuclear explosion resembling a Type 1, a supernova, although its origin differs profoundly from those that illuminated the earlier universe. According to Kaplan's calculations, these extraordinary explosions begin after roughly 10 to the 1,100th years. The number is so immense that writing every digit would require a sequence longer than the width of today's observable universe measured in meters. Even then, the detonations do not happen simultaneously. The most massive black dwarfs explode first, while less massive remnants require even longer before their own pycnonuclear reactions complete the same progression. Each explosion lasts only days or weeks. Compared with the ages preceding it, the event is almost instantaneous. A brilliant flash briefly returns to a universe that has gone without ordinary starlight for incomprehensible spans of time, marking one final stellar detonation before darkness once again becomes the prevailing condition across the remaining cosmos. If we wish to point toward the final enduring object shaped by ordinary stellar evolution, our search would end with a remarkably modest remnant. It would not descend from a giant star or an exotic cosmic collision. Instead, It would trace its ancestry to one of the smallest stars capable of sustaining hydrogen fusion, a red dwarf much like Proxima Centauri, containing about 0.12 times the mass of the Sun. Such a star is expected to continue burning for roughly 4 trillion years before beginning the long transformation already familiar to us. Only after that extraordinary lifetime ends does the remnant begin its own separate journey. The exhausted red dwarf contracts into a white dwarf, carrying less mass than the future remnant of our own Sun. An unexpected rule of quantum physics now becomes apparent. Lower mass white dwarfs are actually larger than heavier ones because electron degeneracy pressure produces an inverse relationship between mass and radius. Removing mass allows the star to occupy slightly more space rather than less. Across ages beyond ordinary imagination, that comparatively large white dwarf releases its remaining heat more gradually than its denser relatives. Its lower density and extended cooling history delay the arrival of its final state until nearly every other comparable remnant has already completed the same transition. By the time it becomes a black dwarf, its mass has settled at approximately 0.17 times the mass of the Sun, close to the smallest theoretical mass capable of producing a stable white dwarf through ordinary stellar evolution. Its diameter spans roughly twice that of Earth. Beneath its dark surface lies a completely solid interior, a crystalline structure composed primarily of carbon and oxygen. During earlier stages, heavier elements slowly migrated inward under the influence of gravity. Those trace ingredients now rest near the center, preserving a layered history written across unimaginable stretches of time. Its temperature differs from the surrounding universe by only tiny fractions of a degree above absolute zero. Any remaining warmth has almost entirely vanished. Thermal radiation has become so faint that the remnant blends into the cosmic background, distinguished only by its gravity and the enduring arrangement of matter maintained through electron degeneracy pressure. Where would you find such an object? Almost certainly not within any recognizable galaxy. Long before reaching this state, gravitational encounters would have carried it into intergalactic space. It continues along a nearly straight path established ages earlier, traveling through an expanding universe where no neighboring structures of similar complexity remain nearby. In many respects, it represents the final object that can still be identified as the product of ordinary stellar history. Mountains, oceans, planets, stars, galaxies, and even the immense black holes of former galactic centers belong to earlier chapters. This black dwarf remains as one of the last recognizable physical structures assembled through familiar astrophysical processes. Yet its story has not completely ended. Deep within the crystalline interior, extraordinarily rare pycnonuclear reactions continue at a pace beyond ordinary comprehension. One nucleus after another changes through quantum tunneling across intervals so immense that even this final remnant carries within itself the distant possibility of one last transformation before the universe settles into an even simpler future. The final transformation unfolds with astonishing speed when measured against the age that precedes it. After waiting approximately 10 to the 1,100th years, the decisive collapse itself occupies only moments. Nearly the entire history of the black dwarf has been an exercise in patience. Its ending arrives almost instantly. Deep within the crystalline interior, pycnonuclear reactions have gradually assembled an iron core, one atomic nucleus at a time. For ages beyond comprehension, that growing center remained too small to disturb the surrounding structure. Eventually, however, The accumulated iron reaches the point where electron degeneracy pressure can no longer sustain the increasing weight pressing inward. Collapse begins immediately. The central region contracts under its own gravity, drawing surrounding layers inward with accelerating force. As the collapsing core compresses the overlying material, temperatures rise dramatically despite the object having spent nearly its entire existence at temperatures scarcely distinguishable from absolute zero. Conditions capable of supporting explosive nuclear reactions suddenly return after an interval longer than every previous era of cosmic history combined. The result is a thermonuclear detonation. Runaway fusion races through the compressed outer layers, releasing enormous quantities of energy in a fraction of the time required to prepare the event. A powerful shock wave surges outward through the ancient crystalline structure, tearing apart matter that remained intact across almost inconceivable expanses of time. The black dwarf ceases to exist as a single object. Its contents expand rapidly into the surrounding void. Carbon, oxygen, iron, and small amounts of heavier elements disperse across immense distances, beginning another journey that no longer belongs to stars. The explosion also releases an expanding sphere of radiation containing visible light, high energy X rays, gamma rays, neutrinos, and countless other particles, all moving outward at the speed of light through an almost featureless universe. No observer witnesses the flash. No planets remain in orbit nearby. No telescopes survive to collect its light. There are no civilizations waiting across neighboring galaxies, because neighboring galaxies have long since vanished as meaningful structures. The radiation simply continues outward, crossing unimaginable distances without encountering anything capable of giving the event lasting consequence beyond the physical propagation of its energy. The scattered matter also follows independent paths. Individual atoms and smaller particles drift ever farther apart as cosmic expansion continues. Their energies steadily diminish while the universe approaches an increasingly uniform state. Differences in temperature become progressively smaller. Opportunities for new structures become progressively fewer. If protons remain fundamentally stable and never undergo spontaneous decay, this explosion represents the last event of stellar significance the universe will ever produce. No later process assembles comparable complexity or releases comparable energy through ordinary matter. What remains afterward is neither a collapsed universe nor an empty one. Electrons, positrons, photons, neutrinos, and diffuse matter persist across the vastness of space, distributed with extraordinary uniformity. The machinery that once built stars, galaxies, planets, and ultimately black dwarfs has completed its work, leaving behind a cosmos where every remaining particle simply continues its endless journey through time. When we step back from every individual star, every remnant, and every immense span of time, an unexpected pattern comes into focus. The transformation from a drifting cloud of hydrogen to a living star, to a white dwarf, to a black dwarf, and finally to a dispersed sea of particles is not a chain of unrelated events. It is the continuous expression of one physical principle, operating without exception, from beginning to end. That principle is the second law of thermodynamics. In simple terms, it states that the entropy of a closed system always increases or remains unchanged. Entropy is often described as a measure of disorder, although another useful way to understand it is as the gradual spreading of energy into forms that become less capable of performing useful work. Once energy has dispersed, nature provides no ordinary path for gathering it back into the concentrated arrangements that existed before. Every process we have followed contributes to that accounting. Nuclear fusion inside stars converts concentrated fuel into radiation. Light escaping from stellar surfaces spreads across expanding space. Collisions redistribute motion. Even the faint release of heat during crystallization and the rare quantum tunneling reactions inside ancient black dwarfs move energy from organized forms toward greater uniformity. Each event increases the universe's total entropy by another small amount. Gravity appears to resist that tendency for a time. By drawing diffuse gas together, it creates stars, planets, and galaxies, producing remarkable islands of structure within an otherwise expanding cosmos. Yet gravity achieves this only while releasing even larger amounts of energy into the surrounding universe. The concentrated objects it builds are temporary because the energy they emit continuously drives the overall increase in entropy. Gravity creates order locally while contributing to greater disorder on the largest scales. Eventually, that long balance reaches its conclusion. Physicists describe the final condition as heat death. The phrase can sound dramatic, yet the underlying idea is remarkably straightforward. Energy has become distributed so evenly that meaningful differences no longer exist. Temperatures are essentially the same everywhere. Density contrasts have disappeared. Pressure differences have faded. Without those gradients, the universe loses the conditions required for change. Every engine depends upon a temperature difference. Every star requires matter gathered into dense regions. Chemical reactions rely upon available free energy capable of driving atoms into new arrangements. Remove those imbalances, and the mechanisms that shaped cosmic history simply cease operating. Nothing dramatic interrupts them. They gradually run out of opportunities to continue. Seen from that perspective, every chapter of this journey belongs to the same unfolding story. The birth of stars, the cooling of white dwarfs, the formation of black dwarfs, the extraordinarily slow nuclear reactions hidden within crystalline interiors, and the final thermonuclear explosion all represent successive increases in entropy. Each marks another completed step in the universe's gradual movement toward equilibrium. The black dwarf was never an isolated curiosity. It was the final enduring structure assembled by familiar stellar physics before the last remaining imbalance disappeared. The concluding supernova became the final luminous entry in a cosmic ledger that had been accumulating since the first stars ignited, after which the universe continued onward with nothing left to reorganize, only energy completing its endless journey toward perfect equilibrium. Even after every familiar source of activity has faded, the story may refuse to end as neatly as we expect. Heat death describes a universe that has reached maximum entropy, where useful energy differences have disappeared. Yet, the laws of quantum mechanics introduce one final possibility, one that belongs less to astronomy than to the deepest foundations of physics itself. Quantum fluctuations remain part of that picture. According to the Heisenberg uncertainty principle, certain properties of nature cannot possess perfectly fixed values simultaneously. As a consequence, tiny probabilistic changes continue to exist even in conditions approaching complete equilibrium. They do not violate physical law. They are permitted by it, arising naturally from the quantum description of reality rather than from any external disturbance. For any single moment, the probability of an extraordinary fluctuation is unimaginably small. A handful of particles might briefly arrange themselves in an unusual pattern before dispersing again. Larger fluctuations become vastly less likely, yet probability behaves differently when paired with limitless opportunity. If space extends without bound, or if time continues forever, Events with incredibly small individual chances eventually become expected somewhere across that immense stage. This line of reasoning leads to one of the most unusual ideas in modern physics, known as the Boltzmann brain. The concept traces back to the work of physicist Ludwig Boltzmann, whose studies of statistical mechanics explored how ordered states emerge from the countless microscopic arrangements of matter. Later, physicists extended those ideas into a remarkable thought experiment. Could a complete, self aware mind briefly assemble through an exceptionally rare quantum fluctuation within a universe that had otherwise reached maximum entropy? If such an event occurred, the resulting consciousness would not experience itself as newly created. It could possess apparent memories, a sense of personal history, familiar places, and even the conviction that it had lived through an ordinary lifetime. Those experiences would arise from the temporary arrangement of particles rather than from actual events. Moments later, the fluctuation would dissolve, and the structure supporting that awareness would disappear as quickly as it formed. The unsettling implication reaches beyond cosmology. If random observers produced by quantum fluctuations eventually outnumber observers formed through billions of years of stellar and biological evolution, then statistical reasoning appears to suggest that most conscious experiences across all of cosmic history belong to those fleeting minds rather than to civilizations like ours. That conclusion feels profoundly counterintuitive, yet it follows from assumptions that many physical theories otherwise accept. No accepted solution currently resolves this paradox. It remains an open question resting at the intersection of thermodynamics, quantum mechanics, cosmology, and the philosophy of mind. Physicists continue debating whether some deeper principle prevents such observers from dominating the statistics, or whether our understanding of the universe remains incomplete in some fundamental way. So, even after the last black dwarf has vanished and entropy has completed its long ascent, the possibility of experience itself may not be entirely extinguished. Across immeasurable expanses of space and endless ages of time, the universe may still permit the rarest imaginable flickers of awareness, appearing for only an instant before returning once more to equilibrium. For almost this entire journey, we have followed one particular future. It is the future in which the expansion of the universe continues steadily, allowing stars to fade, black dwarfs to form, and entropy to complete its gradual work. Yet every step along that path rests upon a single assumption whose ultimate truth remains unknown. It concerns the nature of dark energy, the mysterious component driving the accelerating expansion of the cosmos. The scenario leading to heat death assumes that dark energy behaves as a cosmological constant. In plain language, this means its energy density remains unchanged as the universe grows larger. Space continues expanding at an ever increasing rate, yet the underlying strength of dark energy itself does not evolve. Under this picture, the distant future unfolds much as we have described, with cooling, isolation, and eventual equilibrium defining the final chapters. Present observations are broadly consistent with that interpretation. Even so, they do not exclude every alternative. The remaining uncertainties in today's measurements leave room for other possibilities that obey known physics while producing dramatically different endings. Cosmologists continue testing those alternatives because the available evidence has not yet delivered a definitive answer. One possibility is known as phantom dark energy. In these models, the influence of dark energy strengthens over time instead of remaining fixed. Expansion accelerates ever more rapidly until gravity, electromagnetism, and even the forces binding atomic nuclei can no longer resist it. This hypothetical conclusion is called the Big Rip. Roughly 200 million years before the end, galaxies would come apart. Around 3 months before the final moment, planetary systems would no longer remain gravitationally bound. Minutes before the conclusion, planets themselves would disintegrate. During approximately the final 10 to the negative 19th seconds, even atoms would be torn apart by the relentless expansion of space. If that picture proves correct, no black dwarf ever completes its extraordinary cooling journey. The universe reaches its conclusion long before those ancient remnants can become the final stellar objects we have followed. Another possibility moves in the opposite direction. If dark energy eventually disappears or reverses sign, cosmic expansion could slow, halt, and ultimately reverse. The universe would contract toward an increasingly dense state in a scenario often called the Big Crunch. Instead of endless expansion, cosmic history would curve back toward conditions resembling the earliest moments after the Big Bang. Recent observations have made this question even more intriguing. During the year 2024, the Dark Energy Spectroscopic Instrument released results showing mild hints that dark energy may evolve over time rather than remaining perfectly constant. Those findings generated considerable discussion throughout the cosmological community, but they fell well short of establishing a new consensus, and additional observations are required before any conclusion can be drawn. The most accurate answer today is therefore an admission of uncertainty. The black dwarf future remains the leading long-term scenario because current evidence still favors a stable cosmological constant. Yet nature has not revealed its final decision. The last dead star exists precisely where established knowledge meets unanswered questions, reminding us that even at the greatest imaginable distances in time, discovery remains unfinished. Our own star occupies only a modest place within the broader universe, yet its future gives every distant prediction a familiar anchor. After following the fate of countless stars across unimaginable ages, we arrive once more at the Sun. Its ending is neither exceptional nor mysterious. It can be traced through stellar evolution models built from its measured mass, composition, and present behavior, allowing us to glimpse the legacy it will eventually leave behind. Approximately 7.5 billion years from now, the Sun will complete its evolution into a white dwarf. What remains will contain roughly 0.54 times the Sun's current mass, compressed into a sphere comparable in size to Earth. At first, this remnant will possess a surface temperature approaching 180,000 degrees Fahrenheit, radiating an intense white glow before gradually fading through every stage of visible light. Trillions of years later, its remaining energy will emerge mostly as infrared radiation, continuing its long decline toward complete thermal equilibrium. The familiar architecture of the solar system will not accompany it. Mercury and Venus disappear during the Sun's swollen red giant phase. Earth is expected to be engulfed or rendered completely uninhabitable before the planetary nebula forms. Farther outward, the giant planets and their moons lose the stable gravitational environment they once shared. Some worlds may escape into interstellar space, while others experience disruptive encounters that erase the orderly arrangement existing today. Asteroids, comets, and smaller bodies follow similarly uncertain paths until the solar system no longer survives as a recognizable family of objects. Even the atoms composing Earth's ancient oceans continue their own separate histories. The hydrogen within those waters originated during the earliest moments after the Big Bang. Their oxygen formed later inside massive stars that lived and died long before the Sun existed. As the Sun sheds its outer layers into a planetary nebula, many of those same atoms return to interstellar space, joining material that may someday participate in entirely new generations of stars wherever star formation still remains possible. The white dwarf left behind outlives every companion that once circled it. Across trillions of years, crystallization steadily transforms its carbon and oxygen interior into a rigid lattice extending throughout the remnant. Preserved within that crystalline structure is the elemental outcome of nearly 10 billion years of hydrogen fusion, a lasting record of the ordinary processes that sustained a stable star for almost the entire history of life on Earth. Eventually, even that record ceases to radiate detectable warmth. The white dwarf completes its descent into a black dwarf, carrying no visible reminder of the star that once illuminated blue skies, drove weather across a living planet, and supplied the steady energy that allowed chemistry to become biology. Its final legacy is neither brilliance nor spectacle, but endurance, remaining long after everything that once depended upon its light has passed into history. There comes a point in this journey where the numbers themselves become part of the story. Long before we reach the limits of physics, we encounter the limits of human intuition. We can write these immense spans of time, compare them mathematically, and reason about them with confidence. Experiencing their true scale is another matter entirely. Recorded human history stretches back approximately 10,000 years, from the earliest cities of Mesopotamia to the present day. Entire civilizations have risen and fallen within that interval. Languages have emerged, transformed, and disappeared. Every discovery, every work of art, every scientific breakthrough, and every generation that has ever known the night sky belongs to that remarkably brief chapter. The universe itself is approximately 13,800,000,000 years old. That already exceeds the entire history of civilization by roughly 1,380,000 times. Even this comparison begins to strain ordinary imagination, yet it still describes only the opening pages of cosmic history. The first genuine black dwarfs do not appear until approximately 1 quadrillion years have passed, around 72,000 times longer than the universe has existed today. Then the scale changes once again. The final black dwarf supernova is expected to occur after approximately 10 to the 1,100th years. That number cannot be translated into an everyday comparison because every familiar analogy reaches its limit long before approaching it. Even writing the complete number in ordinary decimal notation would require more digits than there are atoms within the observable universe. Mathematics allows us to describe such quantities precisely, while the human mind finds no comparable experience to attach to them. That limitation is hardly surprising. Our ancestors evolved to judge changing seasons, recognize familiar faces, remember landscapes, and anticipate dangers unfolding across days, years, and perhaps decades. Nothing in our evolutionary history prepared the brain to develop genuine intuition for intervals extending beyond trillions of years, much less numbers whose written form exceeds the available matter required to record them. Consider what that means for everything we have witnessed so far. Every galaxy that has formed, every star that has illuminated surrounding planets, every black hole, every element forged within stellar cores, every living organism, and every conscious observer all exist within the earliest fraction of the universe's eventual lifetime. Relative to the age of the final black dwarf, the entire history we presently know occupies a span so tiny that the distinction between the beginning of the cosmos and this very moment almost disappears. We often imagine ourselves living somewhere near the middle of an ancient universe, The mathematics tells a different story. By the timescale governing the last surviving stars, we remain astonishingly close to the opening moments of cosmic history. The universe is still profoundly young, and somehow, during this remarkably early chapter, you and I have the extraordinary opportunity to look upward and understand even a small part of the immense future still written into the laws of nature. Before we leave the realm of distant stars, consider something much closer. Every atom making up your body carries a history that reaches far beyond the birth of Earth and even beyond the formation of the Sun. The chemistry that allows you to listen, think, and wonder tonight began long before our solar system existed, assembled across successive generations of cosmic change. The oldest atoms within you are hydrogen. Nearly every hydrogen atom in your body, whether bound inside water or incorporated into countless biological molecules, formed during the first 3 minutes after the Big Bang. They have endured through almost the entire history of the universe without ever passing through the core of a star. Those tiny nuclei are among the most ancient, surviving pieces of ordinary matter that exist anywhere. Carbon tells a different story. Every carbon atom woven into your cells and deoxyribonucleic acid originated inside a massive star that lived much faster than the sun. Such stars consume their hydrogen over only millions of years before progressing through heavier stages of nuclear fusion. When their fuel is exhausted, gravity overwhelms the core, producing a core collapse supernova that scatters newly forged elements across surrounding space. Long before our solar system formed, those explosions enriched enormous clouds of gas with the carbon that would eventually become part of you. The oxygen entering your lungs followed a remarkably similar path. It, too, emerged from the intensely hot interiors of massive stars before violent supernova explosions dispersed it into the interstellar medium. Every breath connects your present life to stellar furnaces that vanished billions of years before Earth existed. Iron carries perhaps the most dramatic origin of all. Inside a massive star, fusion releases energy only while creating elements lighter than iron. Producing iron itself requires energy instead of providing it, marking the final stage before gravitational collapse becomes unavoidable. During the last moments of that collapsing core, enormous temperatures and pressures complete the formation of iron, which is then expelled into space by the supernova explosion. The iron circulating through your blood today began its journey during those final catastrophic seconds. You are therefore not observing the universe as something separate from yourself. The matter composing your body has already belonged to ancient stars, expanding nebulae, molecular clouds, planetary surfaces, oceans, and living organisms before arriving in its present arrangement. In time, those same atoms will continue onward once again, returning first to Earth, then ultimately to the material expelled by the aging sun, and eventually becoming part of the wider interstellar medium. For a brief interval within an extraordinarily young universe, those ancient atoms have become capable of asking where they came from and where they are going. That temporary arrangement does not stand apart from the cosmos. It is one expression of the cosmos itself, assembled from its own enduring material, reflecting upon a history written across billions of years and extending into a future almost beyond comprehension. There is one part of this story that physics can describe only from the outside. Equations can predict how stars ignite, how galaxies evolve, and how black dwarfs eventually meet their end across astonishing expanses of time. They can follow matter and energy with extraordinary precision. Yet they do not explain why any of those events should ever be experienced by an aware mind observing the universe from within. Current estimates suggest that the observable universe contains roughly 10 to the 24th stars. That number exceeds the total count of grains of sand scattered across every beach and desert on Earth. Nearly all of those stars have burned, without leaving any evidence that someone was present to witness their light. As far as present science can establish, conscious awareness has emerged with certainty on at least one small rocky planet circling one ordinary star within one ordinary galaxy. Whether life exists elsewhere remains among the greatest unanswered questions in astronomy. The search continues through studies of planetary atmospheres, investigations of potentially habitable worlds, and the ongoing search for technological civilizations. Even if living worlds are abundant throughout the cosmos, the proportion of all matter that has ever participated in a conscious experience remains almost unimaginably small when compared with the universe as a whole. The timing is equally remarkable. The era in which stars actively shine and planets can maintain conditions favorable for complex chemistry extends for approximately 100 trillion years. Compared with the immense future leading toward the last black dwarf and beyond, even that enormous interval occupies only the earliest portion of cosmic history. Nearly everything that biology requires belongs to the opening movement of a universe whose later ages become increasingly uniform. That places us within an extraordinarily unusual chapter. We are living while stars still transform hydrogen into heavier elements, while planets remain warm enough for oceans, atmospheres, and evolving ecosystems, and while light continues crossing galaxies filled with active stellar nurseries. On the timescale governing the full lifetime of the cosmos, this interval passes with remarkable speed. Imagine viewing the complete history of the universe at once. The ages that follow the final black dwarf contain vast stretches during which no known process assembles new living worlds. No familiar star rises over a planetary horizon, and no ordinary chemistry supports minds capable of asking where they came from. Whatever awareness exists across the lifetime of the cosmos is therefore concentrated near its beginning during this comparatively brief era when complexity flourishes. That realization returns us, unexpectedly, to the present. You are hearing these words because ancient atoms became living cells became curious minds, and curious minds learned how to understand the stars that created them. Against the backdrop of everything that follows, the ability of the universe to know even a small part of itself through conscious experience may be among the rarest phenomena it ever brings into existence. And for this brief moment, it is happening now. One question remains after following the universe so far into its future. If every star eventually fades, if every civilization disappears, and if no observer survives to remember what came before, does anything that happened retain significance? It is a question that seems philosophical at first, yet physics offers an unexpected perspective rooted in the irreversible nature of time itself. The second law of thermodynamics tells us that every natural process increases the total entropy of the universe or leaves it unchanged. That increase cannot simply be reversed. Once an event has occurred, the universe cannot return to the exact state that existed before it. The arrow of time points in only one direction because every interaction leaves consequences that become part of everything that follows. Consider the sunlight reaching your skin only minutes after leaving the sun. That encounter transfers energy, alters molecules, and changes the microscopic arrangement of matter in ways that continue propagating through countless later interactions. Every consequence produces further consequences. The original event cannot be removed from history because the universe itself has already incorporated its effects into the unfolding chain of cause and effect. The same principle applies across cosmic history. A star that spends approximately 10 billion years converting hydrogen into heavier elements permanently changes its surroundings. Its light travels outward across space. Its stellar wind enriches nearby gas. The elements forged within its core become ingredients for future planets, future chemistry, and perhaps future living organisms. Although the star eventually dies, the changes it introduced remain embedded within every process that inherited its material and energy. When that star becomes a white dwarf, its crystallized interior preserves the physical outcome of billions of years of nuclear fusion. The orderly lattice of carbon and oxygen reflects the entire evolutionary path that produced it. Even after the remnant ultimately reaches its final transformation, the redistributed matter and released energy continue influencing the universe that succeeds it. The last black dwarf supernova follows the same rule. No observer need witness the explosion for it to matter physically. Its expanding radiation, scattered elements, and altered distribution of energy become permanent features of the universe's subsequent state. Every particle emerging from that final detonation carries forward the consequences of an event that can never be erased, even if no consciousness remains to describe it. Physics, therefore, suggests that nothing is forgotten in the thermodynamic sense. The past is not preserved inside a hidden archive waiting to be rediscovered. Instead, it survives because every event reshapes the conditions from which every later event emerges. History becomes inseparable from the present through an unbroken chain of causation extending across all of cosmic time. Perhaps meaning does not depend upon lasting memory after all. Perhaps it depends upon lasting influence. Every star, every planet, every living creature, every thought, and every moment permanently alters the universe that follows. The future carries those accumulated consequences forward without exception, making the past the one part of reality that can never be undone. There is one truth that deserves to be spoken plainly before our journey comes to its close. We exist during the richest chapter the universe is ever expected to know. Across the observable cosmos, roughly 100 billion galaxies continue shining at the same time. Within each of those galaxies reside hundreds of billions of stars, each one transforming hydrogen into heavier elements, while sending light and warmth across immense distances measured in light years. Taken together, these countless stellar furnaces create a universe of extraordinary variety. Galaxies collide and grow. New stars emerge from cold molecular clouds. Planets circle stable suns. Black holes shape their surroundings. Nebulae glow with freshly enriched gas. At no other known stage does the cosmos display such an abundance of distinct structures existing simultaneously. The universe has become more chemically diverse and more structurally intricate than at any earlier time, while every prediction suggests that this complexity will gradually diminish across the unimaginable ages ahead. The timing of our existence makes all the difference. Life requires far more than energy alone. It depends upon liquid water, long-lived stars, stable planetary environments, and a rich supply of heavy elements such as carbon, oxygen, phosphorus, calcium, and iron. Those ingredients did not exist immediately after the Big Bang. They accumulated only after multiple generations of stars lived, fused new elements within their cores, and returned them to interstellar space through stellar winds and supernova explosions. We therefore arrive during an unusually favorable interval. The first stars had already completed their work of enriching the cosmos. The Milky Way had gathered enough heavy elements to assemble rocky planets. Stable stellar systems capable of supporting complex chemistry had become widespread. Yet the long decline of the stelliferous era, the age when stars actively shine, remains only in its earliest stages. We stand at the intersection of those two remarkable circumstances. Look upward on a clear night, and the familiar pattern above you may seem timeless. It is anything but. Every bright point visible to your eyes belongs to a fleeting season of cosmic history. On the timescales we have explored together, even the longest lived stars visible from Earth occupy only a brief opening passage before the universe settles into far simpler conditions. Imagine that same view 100 trillion years from now. Newly born observers, if any still exist by then, would never witness a sky overflowing with brilliant neighboring stars. Most stellar nurseries would have vanished. The familiar constellations would have dissolved beyond recognition. The extraordinary abundance surrounding us tonight would already belong to an ancient past. This moment, wherever you happen to be listening, exists during the universe's greatest flourishing of light, chemistry, structure, and possibility. You are present while stars still illuminate countless worlds, while galaxies remain vibrant with activity, and while the cosmos continues creating the conditions from which awareness can emerge. In the immense history of everything, that is an astonishingly fortunate time to be alive. Throughout this journey, one object has remained on the distant horizon, waiting beyond every star, every galaxy, and every familiar measure of time. The black dwarf is more than the final stage of stellar evolution. It is the destination toward which an ordinary star, shining somewhere in the sky tonight, has already begun its unimaginably long passage. Even now, countless small red dwarfs continue burning their hydrogen with remarkable patience, unaware in any physical sense that one among them may someday become the last surviving stellar remnant in existence. That future remnant will endure beyond the galaxy that gave it birth. Long after gravitational encounters scatter the remaining stars, and the familiar shape of its home has disappeared, it will continue drifting through an expanding universe where galaxies themselves have faded beyond one another's horizons. Across quadrillions of years, its fading white dwarf interior will crystallize into an immense lattice of carbon and oxygen, preserving the outcome of an evolutionary process that began when hydrogen first ignited within its core. Around it, the universe will continue cooling toward temperatures lower than anything ever measured inside the most advanced laboratories of human civilization. Every known natural environment existing today will seem comparatively warm, yet that ancient black dwarf, though only fractionally above absolute zero, will still remain ever so slightly warmer than the vast emptiness surrounding it. The difference becomes almost meaningless numerically while remaining physically real. Within that crystalline remnant, quantum tunneling continues its patient work. Quantum tunneling is the phenomenon in which particles occasionally pass through energy barriers that classical physics would forbid. Across spans of time so immense they overwhelm ordinary language, isolated fusion events gradually assemble heavier nuclei deep inside the compressed interior. The process never rushes. It simply follows the probabilities written into the laws of nature from the beginning. Eventually, those accumulated changes reshape the star one final time. The last black dwarf reaches the conditions required for its ultimate thermonuclear explosion, releasing light across every direction into a universe containing no known observers to receive it. Even without witnesses, the event remains every bit as real as the first starlight that illuminated the young cosmos billions of years after the Big Bang. Seen from this perspective, the black dwarf does not represent futility. It represents completion. The same physical laws that assembled hydrogen during the earliest moments of cosmic history guided the birth of stars, the creation of heavy elements, the formation of planets, and the emergence of living beings capable of understanding those processes. They continue operating with unwavering consistency until the final stellar remnant fulfills the last step available to it. The universe, through nothing more than the persistent operation of its own laws, carried a single story from its opening moments to its closing chapter. The last black dwarf becomes its final sentence, completing a narrative written across almost inconceivable expanses of time. After that ending, no further chapter follows. Yet everything that came before remains part of a history that truly happened, leaving an irreversible imprint upon the universe that continues forever. We return at last to the present, not because the future has ended, but because this moment is where every distant prediction begins. The black dwarf belongs to an age so remote that it almost resembles mythology. Yet it is no legend. It follows directly from the same physical laws governing the stars above us tonight. Throughout the Milky Way, approximately 10 billion white dwarfs already continue their gradual cooling, each one advancing along a path that leads toward that final state if time allows. The very last black dwarf has not even begun its existence. Somewhere within an ordinary region of our galaxy, its progenitor still shines as an unassuming red dwarf, steadily converting hydrogen into helium at a pace so slow that its future stretches beyond almost every number the human mind can meaningfully imagine. Nothing distinguishes it from countless similar stars. It simply continues the work that gravity and nuclear fusion began long ago. Look upward whenever the sky allows, and every visible star occupies a different chapter of its own history. Some have only recently formed from collapsing clouds of gas and dust. Others approach the closing stages of lives measured across billions of years. A few have already completed their evolution, leaving compact remnants hidden among brighter neighbors. None will endure forever, yet each contributes something unique to the continuing evolution of the cosmos. Everything we have explored points toward a universe that ultimately becomes colder, simpler, and increasingly uniform. That outcome is not a failure of nature. It is the inevitable conclusion of the most intricate sequence of physical processes known to science, beginning with the first moments after the Big Bang and unfolding through generations of stars, planets, chemistry, and life. Every stage follows naturally from the one before it. Our place within that sequence remains astonishingly early. We exist while galaxies continue forming stars, while heavy elements circulate through interstellar clouds, and while living worlds still possess oceans, atmospheres, and the energy required for biological complexity. The final black dwarf belongs to an era when every familiar question has already faded from the universe. But those questions have not disappeared today. They continue wherever curious minds turn toward the night sky and wonder how everything began, where it is going, and what our place might be within such an immense story. The answers remain incomplete, yet the search itself is part of the universe's unfolding history. As you listen now, stars continue shining across the Milky Way. Light leaves their surfaces and begins new journeys through space. Ordinary atoms continue becoming extraordinary structures capable of curiosity and understanding. The future we have imagined is unimaginably distant. This present moment is real, measurable, and filled with the remarkable conditions that make such understanding possible. The stars are still burning, and for now, so are we.